Hey guys, I figured I'd record this week's discussion post since we were given that opportunity. So, my apologies in advance if I sound a little bit rough. I'm unfortunately still recovering from the flu. So, my content area is physics, and I actually think physics already lends itself quite well to content area literacy. A lot of what we do in physics requires students to read, interpret, and communicate information in ways that are specific to physics and astronomy. In the readings this week, it really helped me put a better language to the things that I think many physics teachers are already doing intuitively in their own classrooms. At the high school level, students typically use a textbook in physics class, as they likely do with many of their other coursework material, which immediately brings in literacy skills like reading comprehension and diagram interpretation. But physics literacy is almost like a language of its own. We work with vectors and free body diagrams, and we do a lot of multidimensional analysis. And there is a whole lot of symbolic representation in physics, which is kind of unique from a lot of the other fields, all of which it's usually tied to a descriptive text. And for example, you'll see a lot of that in my textbook here, which I'll actually show you. Here, for example, you'll see written explanations, and they're almost always accompanied alongside either a graphic or some type of vector diagram like shown here. And students have to read that text portion, and they also have to interpret those diagrams that are shown to completely understand what's being represented here and what the symbols are each representing, like the small m or the W for weight in this case, and the M for the mass of the basketball. And that aligns directly with the readings idea that each discipline has its own structures and representations, and literacy is how those students make sense of all of that. In physics specifically, we also use a lot of abstract symbols, often Greek letters, and those can be quite daunting at first for students. But there's a good reason that we use those symbols, and it's not just for historical purposes. These help us physicists represent physical quantities and variables in distinct and concise ways for both accuracy and efficiency, respectively. And these symbols, they're essentially vocabulary terms for students. And students have to know that words like work, power, or momentum, they mean something that is very different in physics than they do in everyday language. And that's one of the things that the readings really emphasized is the importance of helping students distinguish that, the difference between everyday meanings and scientific meanings. And in physics, it's all full of those types of traps. So it's really important that as teachers, as physics teachers especially, we help students understand those differences. So literacy in physics, it's really about helping students think and reason and, and communicate in the language that us physicists use, and not just to plug it numbers in, like I said, and like they're just plugging it into a formula to try to get an output from it. Even physics problems, especially on standardized testing, they're almost always presented as word problems, which makes physics literacy very distinct from your typical math course. For example, we can just look at some of the AP exams that are offered every single year. I printed them out just because I like to do them for fun in my free time. So I think one of the AP tests that demonstrates this the best is AP Physics 1, last year's 2025 test. Eh, Specifically question number 4 with the scuba diver. So students are presented with this really fantastic pictorial description of what's going on, but then also in textual format, they're given a description of the scenario, and they're not even given any numerical values for this entire problem, actually. All they're given is just relative density differences, and the students are then asked to describe what's going to happen in terms of buoyancy to that scuba diver holding that block, that mass block. In fact, they're actually asked to simply provide a qualitative reasoning, meaning just a text description of what's happening with this, what's going to happen with this scuba diver in terms of his acceleration up or down, depending on how the buoyancy of the water changes. So it really shows that the students have to be able to comprehend text, identify relative information from that text, and interpret the diagrams and graphs if they're provided with graphs. And a lot of these questions do provide them with that. And then they have to oftentimes, Like in this exact example, they have to justify their reasoning in writing. And that directly supports what the readings were pointing at, that literacy really does improve our conceptual understanding and our critical thinking, not just test performance, although it will directly tie to that, especially in physics. And as you can see, almost all of these physics problems, they're all word problems. And that's something that is really unique with physics. Almost everything here, actually everything here is a word problem. It all starts with a text description. And sometimes they give you numbers and sometimes they don't. And the students have to decipher that text and then justify their reasoning. Sometimes with equations and sometimes with text. This also closely mirrors how actual real scientists work and how they discover and stay up to date with topics in their field. Scientific papers, they're typically paragraphs of text, and I'm sure you have all have read them before. And they're oftentimes accompanied with graphs or diagrams, and oftentimes images from their experiment or meta-analysis or whatever they're performing. And those are all included to help support and explain the text. And the text is there to not only justify the claims that the scientists are making, but also try to make the experiment or the meta-analysis repeatable from other scientists to verify their work. So literacy skills in science, um, it really helps students practice, especially in physics, and it's very transferable to other scientific fields, especially when they get out to and start doing their own real scientific work. In my own physics classroom, I actually plan on intentionally strengthening some content area literacy in both explicit and also engaging ways. For example, I want to introduce new lessons every time I have a new topic with a little bit of snippets from a book called The Cartoon Guide to Physics, which I actually have right here. It's actually a really great book. It uses humor in a really clever way, and it uses cartoons in a really clever way to help explain some really complex ideas. For example, like the four basic forces um, in nature. And this is was always one of my favorite books in middle school when I really started to get into physics. And I think it would be really fun to give students multiple entry points to connect with the content area literacy, especially through this type of visual representation. And I think it's a really great low pressure way to try and hook students while still providing some textual interpretation, just in a lot more accessible, fun, and engaging way, especially as a hook to the very beginning of class time. A more explicit example that I'm going to be giving students will be a short article from Skydiving Paris. I found it about physics on terminal velocity specifically, which is going to tie in great to a project that I'm actually already going to be having students doing. Students are going to annotate text from a printed out article that I'll provide them as part of their homework assignment for that night. And students would annotate that text and they're going to answer just three short questions. Each of the questions is going to tie back to one of the three Newton's three laws of motion. And I also plan to extend that topic into a collaborative discussion, a class-wide discussion, since collaboration oftentimes mirrors how real science works. For example, there's something called a NASA Roses. It's a mission concept proposal process that they go through. And what they do is they essentially invite scientists in to propose mission ideas. And each of those ideas is reviewed and debated by expert panels, and they evaluate the science and the feasibility and the cost of each of the scientists' ideas. And then scientists from NASA will ultimately decide which of those missions get funded. In fact, I'm actually even considering running a capstone project where we actually will do a class-wide simulation of a NASA Roses convention, although I'm not quite sure what that will look like yet. I also plan on extending the skydiving topic into a cross-disciplinary discussion the next day in class using a Socratic seminar format, where we're going to focus on ethics and safety of parachute design. So, for example, whenever you're manufacturing a parachute, of course, a larger parachute design is going to reduce your terminal velocity, and therefore it's going to create a lower impact speed whenever you eventually hit the surface. But unfortunately, it does increase the force that you experience whenever you first pull that cable and it deploys your parachute. And that really creates an interesting ethical dilemma and an engineering trade-off that I'm going to have students discuss on what they think, and they'll be able to exchange ideas with one another in a peer setting. And we'll also see some of those similar trade-offs in some of our later units, like for example, when we get to momentum in terms of vehicle collisions, bumper designs, roll cages, and how those can be balanced with pedestrian safety. So I think those types of discussions, they really push students to read more carefully, and yet we're always staying grounded in the actual physics content itself. Overall, I think especially for physics, the content area literacy, it's not really something that needs to be tacked on. It's really the foundation, particularly for physics, like I stated in the very beginning. And when they can read and they can write and speak and think like a physicist does, I think they move more from just passive memorization of just formulas and just plugging and chugging numbers to actually real understanding of real life physics phenomenon.